Someone is going to have to help me learn to speak math.
That was
Don't look. What are
yeah,
they?
sorry.
Okay. All right. Well, good evening, everyone. So when I was looking in my inbox and I received the message with my topic, checkmate, I spent some time trying to figure out how the hell am I going to make this apply to chemistry? Because of course my field is chemical engineering, and it was a bit of a stretch, but I'll try and walk you guys through it. Sort of thinking back to when my dad first taught me how to play chess, I was maybe 10 or 11 maybe, and the question came about what exactly is a checkmate? Well, as Mr. Valpy kind of helped me explain earlier, it's a position and an orientation of movable pieces in which one of them cannot move. This is a very simple checkmate. There are further simple checkmates. Of course, here we can see that the king cannot move because of the rook. More complicated ones, but what they all have in common is that there are lots of different movable pieces which are interacting with each other and that could move around in two-dimensional space. Now, I was hunting through the internet for good pictures of checkmate. Of course, the internet has some different ideas about what checkmate constitutes. And I ran across this particular image, which so for those of you who might require some explanation, male washroom etiquette dictates that you use the urinals in such a way that other gents who have to use the facility don't have to stand next to someone. So in the second panel, we can see that this one here with the troll face has positioned himself such that the newly entering orange figure cannot, in fact, avoid this sweaty palm fate. So, but it's funny. But there's a neat story in here. One of the central narratives of material science and chemistry is encapsulated in this picture, and that is that molecules will tend to try and find the most comfortable state for themselves. In this case, this orange guy is not going to get it. Now, I'm going to propose a thought experiment here. So imagine or one of your relatives gave you a puzzle for Christmas in a box, and I told you to shake the box and then open it up after a while and hunt through it for all of the pieces that had randomly been connected in the correct order. You'd maybe find maybe one pair, and I asked you to keep shaking, keep shaking, keep shaking, and I told you to shake it until all of the pieces had randomly rattled themselves into the correct position, ending in a finished puzzle. That would be pretty strange. It would be a very strange outcome. You would not expect for that to happen spontaneously, and spontaneous is the key word here. Now, I was a Lego man when I was, okay, I'm not an actual Lego man, but I played with Legos when I was young. And it's a similar question. I mean, if you were rustling through your Lego box, it would be very strange to come into a situation where just this random movement was creating these finished Lego houses and cars and spaceships and stuff. So keep in mind how strange that is. But the central kind of thesis of the talk tonight is that at the molecular level, you see precisely that happening. And I'm going to try and show some examples of this kind of weird and wonderful behavior of molecules that undergo this process known as self-assembly. Now, I'm going to step off topic, to another facet of my misspent youth, which was Tetris, for another key concept here, and that's the concept of a gradient. And in this case, it's gravity. All the Tetris pieces are falling in one direction. Of course, with molecules, this is happening in 3 dimensions. And unlike Tetris, it can occur from all directions at once. So you can imagine all these pieces coming together to make this nice little Tetris heart here. So that gradient is also essential for self-assembly. You need to have something like temperature, things are cooling down, perhaps shear stress if you're stirring something. There are various other things, but the way you can kind of visualize this, and isn't this not this kid's best day ever? is thousands of tiny little hands kind of working away, fitting your molecules together in kind of a semi-random way, and your job as a chemical engineer is to design your molecules in such a way that even under random motion, they undergo manufacture by thousands of tiny kid hands into useful structures, and I'm going to show you a few examples of those now. So I'm going to start with this one here, and I'm going to go through this as a series of images. If you look closely here, this is a series of silica beads. They're tiny little spheres. The scale bar is 5 micrometers, so 5 millionths of a meter. And you can see that they've arranged themselves in this really nice, orderly, packed manner, sort of if you were stacking cannonballs or something like that. The thing to keep in your head here is that these silica beads are clear, they're transparent, they have no color. This is a closer picture showing salt that's crystallized in between them. These little cubes here are just salt crystals, again, something clear. And yet, when you make a little film evaporated out of water, you get something like this. These are optical photographs, 5mm scale bar, under light. And as you can see, they're beautifully iridescent, similar to a beetle casing or a butterfly's wing. This is precisely what happens in nature with opals. It's the same silica, it's the same water, it's the same salt. So we can engineer, based on the diameter of the silica beads, the range of colors you produce, because the effect is diffraction, so it's the same thing you'd see on oil slicks. I could go into that, it's a bit complicated, but we can create films that self-assemble into these beautiful little layers with minimal processing technique to get beautiful, shiny films. Are there any diabetes sufferers in the audience tonight? None? Okay.
Diabetes researcher.
No? Oh, okay. All right. Well, okay. So all of you are enjoying the benefit of this this particular self-assembly process. It's a self-assembly of proteins. This is an insulin molecule here, and 2 of them will come together naturally by self-assembly to form this dimer here, di for 2, and the 3 of those will come together to make this sort of donut-shaped hexamer of insulin. This is a 3-dimensional model of what the protein looks like, and they form together. They self-assemble into these nice little rod structures here. This little cartoon is showing how they've kind of self-assembled together. And this is on silicon, but your body uses a similar self-assembly process to store insulin inside your body in little vesicles so that it can be compactly stashed and easily accessible. So this is an example of self-assembly in nature being used by a living organism. And I was looking at this photo and it kind of reminded me of stacked donuts. So there's a cruel irony in here somewhere. I'm not quite So I'm going to move on to some molecular diagrams. Now don't freak out on me. I'm going to go through these as comprehensively as I can. These are rotaxanes, so from the Latin to rotate. And God, I really hope I got that right. This, as you can see, is a little wheel around a vertical spoke, the same on the right. And what's strange about these is that these are not ionic or covalent bonds holding these together. This is just pure mechanical interaction. You've got these repelling groups at the end, sort of like a barbell, and the rings stick around there. And it's just like a wheel on an axle. So we find ourselves in an interesting position in this case. We have mechanical forces available at the molecular level, which is unusual. We don't usually get that. We have heat, we have electrons, but we don't usually have mechanical forces. So this kind of proposes the idea of sort of molecular clockwork, and there's all kinds of interesting structures that have been made with multiple rings on wheels and interlocked spokes and systems. It's kind of, I mean, to me it suggests a return to steampunk kind of at the molecular level, so really excited to see what comes out of this. Now this horrifying structure here is known as an incarcerating molecule. It traps things. So this is a system on the left is 2 separate molecules. Benzocyclobutane-dione is the little one with the square in the middle, and I have no idea what the outside one is, how that is pronounced in English. But you melt the 2 of them together by increasing the temperature, and then you cool it down, and the 2 halves kind of come down together and it can't escape. And something interesting happens here. You have very interesting localized chemical conditions, so you can carry out reactions that you would not normally be able to carry out. Similarly to this transformation of Dr. Jonathan Osterman into Dr. Manhattan in the movie Watchmen. Please tell me someone gets that reference. They put him in an enclosed space, they zap him with wizardly blue light, and he turns into a blue, naked, very naked demigod. Interesting moral perspectives. And we get the exact same thing happen here. So the chemists in the audience, for you guys, this is not a typo, this is a triple bond. This is not benzene, this is not your average friendly benzene, this is benzyne. Which is an extraordinarily unstable compound which you could never create in real life just floating around in the atmosphere or have it lying around in a beaker. You need the benefit of this very kind of strange incarcerating molecule to trap it and keep it stable and keep it alive. But sure as day we can see the NMR peaks from it and it's actually being created. So this is really neat. The reason I chose Dr. Osterman is that you zap it with 400 nanometer laser light, which is blue. So and you can see the carbon monoxide coming up. So yes, so we can't do it on the scale of physicists yet, but I hope someday. Okay, so this looks a little freaky, but I'll go through it in segments. And I'm going to talk about, now that we've covered sort of the basis of self-assembly, what would be perhaps referred to as sequential self-assembly, or matryoshka spheres or cages, like the Russian dolls. So this is a nice example of using self-assembly to trap metal cations, so positively charged metal ions. So picture the situation: you have a contaminated field, kind of boggy field on a post-industrial site that's heavily laden with cadmium and other stuff. And getting cadmium out of soil, as any environmental scientist will tell you, is a bitch. But this structure is nicely shaped so that the hollow space inside it is just the right size and charge that, well, in this case, a strontium molecule will love to jump in there, but you can make them in different sizes and grab onto, say, for example, cadmium molecules. And this guy here looks, a little bit freaky, and it curves over into a bowl structure, and the three-dimensional model on the right is two of them interacting. Some, kind of imagine as though you're holding a little bird. You've got something kind of twitchy, gently held between two half spheres. So that at the chemical level is precisely what's happening. So you can make this, this thing here, which is really nicely soluble in water, and this thing here, which is really nicely soluble with surfactants and in oil, and the pore size in here, basically the space inside the hands, is perfectly sized to grab onto one of these. So they were able to show that you can selectively grab up, whatever it is you're using to grab your contaminant molecule, or maybe you're a filthy capitalist and you're going after gold ions or something like that. There's all kinds of applications for this, and you can then scoop that out with a nice non-polar solvent. Yeah, just like holding baby birds. And this is the final example that I kind of want to show you. This is one of my favorite ones. These are called calyx arenes, from the Latin for chalice. They are indeed bowl or bucket shaped, as they're somewhat unromantically referred to in literature. What they look is a little bit like a sea anemone that traps things, or as I like to kind of see it, as a basketball net with a basketball falling through it. And we're in the interesting territory now where we can do size exclusion and very, very fine structural exclusion. So one way, I wish I had some pictures for this, but I'm going to use hand waving instead. One problem is to try and separate molecules with very similar boiling point. You can't fractionally distill them or anything like that, but they have slightly different structures. And if you have one, imagine a basketball, if you will, with two sticky out bits, top and bottom, and one with them sticking out at like 1 and 2 o'clock, and then one at 1 and 7 o'clock, something like that. Separating those out once they're mixed together is extremely difficult. But these little bucket molecules can sort of structurally separate out the ones that are just the ones that are top and bottom with a very, very high degree of selectivity, which is, it's unusual, and I think this is probably the most kind of elegant use of this, because you can use it to, for example, separate out drug molecules or proteins that kind of agglomerate out in circles. Plus, I think the name is really pretty. So this concludes my talk, and yeah, I can take some questions.
Well, just while you're framing your questions in your minds, Trevor, you talked about chemical systems where the equilibrium or checkmate conditions have particularly unusual behaviors.
See what you did there.
Why do the corpses exude?
History. Really. They were exhumed because of these theories that individuals wanted to prove. It was a mass product of exhuming all of the Medici tombs, so not just Eleonora and her sons, but people who had been buried from the 16th up to the 18th century.
And the church went along with this, eh?
Yes. But they were reinterred very respectfully.
Sure.
I have kind of a related question. How, as a historian, do you make the or that it's ethically okay to take out a body or something like that. I mean, because if you do that to someone who's been buried in the last 10 years, everyone's going to think you're psychotic. But obviously, it's very common for, I do medieval work and that happens all the time. So how do you make that decision?
There definitely is sort of an ethical component, and I think it just all has to do about have enough time has passed for it to be respectful, because there is a value in it, which is if we had left these bodies underground forever, for example, if we had decided to dig them up in 2013, the dress might not have even survived. So you have to sort of balance between like gaining perspective or losing perspective, and I think she died in the 16th century, and I think 1857 gave enough sort of respectful distance.
Great presentations.
Yeah.
I have a question for each of you. I'm going to shoot the three of them first, and you guys can decide how you want to answer. I'll start with this order. Trevor, for the Marishikova, what was it called? Matryoshka sphere, the non-polar Matryoshka sphere, could it absorb, like, does it have charged interior molecule, like, is it charged on the interior that it can
I've seen some sort of grabby hands where they have had kind of charged palms, if you will, but
Yeah.
as far as I can tell, most of them are not.
So the non-polar one cannot grab onto charged molecules.
As far as I understand, the problem with making it charged, they tend to sort of fold up on themselves. You need it to be weak enough of a charge, just van der Waals interactions for it to stay nice and open.
Because there's some proteins where they're like inside they're positively charged, and outside they're non-polar.
Yeah.
And they can like dissolve.
Proteins are a whole kind of other tricky field.
Okay, so they're not protein. Okay. And Christina, wondering why the lady had taken a picture with her death robe.
The painting?
Yeah. Like, why did she decide to just wear it and get a portrait of it?
Do you mean the portrait of Eleonora in
Yeah.
the 1560s?
Yeah, yeah. Like there's
I
one.
don't think she knew she was going to die immediately.
Oh, yeah, but like, no, oh, okay. I know that. Like, so what she meant by her death gown or something like that.
No, it wasn't necessarily her death gown when she bought it. It was just the last
Oh,
gown
okay.
that had ever been
So that's what she
made.
meant by that. I thought she meant she bought it for herself to be buried.
Oh,
in.
no.
I feel like dying today.
No, I mean like, you know, she.
That
And I
is
know,
nice.
you know, she wanted to be buried nicely.
Yeah.
And Connor, why were the penalties so light at the end, like 3 years, for example, for the person who directly killed a lot of people?
Well, he was sentenced to death, but he only served 3 years because it got once they put this modification board into place, everything slowed down to a crawl, and there was you know, because then they started reviewing it, their decisions.
So it was like administration was way too slow.
Yeah. So instead of just bang bang bang, a few months later they get hanged, they had to look at all the petitions. There was 3 reviews that had to be conducted, and it just slowed down to crawl. And of course the administration moved slower because of all of this really intense political pressure.
Okay, thanks.
Yes.
My question is to Connor. Having grown up in Japan, I became familiar with the Tokyo Tribunal, and people, especially conservatives like right-wingers, but they are not crazy. Like they are sober enough to be a Tokyo governor, and they claim they raise the evidence that the soldiers were unjustly executed because they committed atrocities, but they were by the order of generals and kind of stuff. And then because of that, the right-wingers claim that was just a retaliation of Allied forces, and this court itself is unjust, and they don't accept even like. And then the ramification of this is that they started justifying it wasn't no like A-class war criminal. And is there something like that in Germany, and how discourse around it is Germany?
Yeah, well, I'll start tackling that issue with because I look at petitions for clemency, and that's one of the biggest issues that's raised. Is they call it victor's justice, and the cries get stronger and stronger as you get further away from 1945. So the later you get, the stronger the calls are. And there were calls of victor's justice from all segments of society, from government, church, politicians, social groups, lobbies. So yeah, there's similar cries too. Although what's interesting is that if you read the transcripts and look at the evidence that were brought forward, at least for the 6 main camp trials, like most of the evidence is pretty overwhelming for the ones they chose, except for, of course, the murky cases like Christoph Noel, who was a functionary.
My question is also for Connor. I think you said that 38 out of 40 in the first round were executed.
36, yeah.
36. I was wondering about those last 4 then, I guess, who managed to escape the execution. Do you know anything about them, what it was about their crimes that weren't bad enough at that time during that atmosphere that they could escape the execution?
Yeah, I gotta think back to, I can't remember exactly what those 4 did. I probably would have at one point. But there were a few that were tried because they tried to be representative, so show staff from all parts of the camp. There were a few people that were there for like a month and then were transferred to the Eastern Front, or worked in an office and claimed that, you know, they never came into contact with the camp at all. And though they still got sentenced, like everyone got sentenced, no one went home after the trial, they didn't get death sentence. But I would have to go back to the transcripts of what they actually did. Sorry.
There's Peter.
Yeah, it's Connor as well. Sorry, buddy. So it's like a broader question. Have you looked at, or do you know of, the way that clemency boards functioned and outside of the U.S. occupied zone? So in the other zones, were there like similar functions, or was it like a different procedure and like timeline by which they would provide a sentence and carry it out?
That is a great question, and I think that'll be the next step for my research, because and there's no literature on the clemency apparatus for these zonal trials. Or like, I think there's in some of the survey histories of, you know, post-war trials, they maybe mention it, but I can't even think of what the apparatus would be in the French zone or the British zone, and certainly in the Soviet zone, it's a whole different ballgame. So that's the next step in this research, is to compare it to other zones and also to compare it to later West German trials and what their clemency apparatus.
John?
Yes, this is for Christina. Your research is so cross-disciplinary. Do you think you've crossed the threshold of history and entered new and uncharted waters? And if so, how would you characterize yourself and your research?
No, I'm a material culture historian, meaning I'm a historian, but I use the apparatus of material culture as a lens by which to go about my research.
I've got a question for Trevor. So you mentioned there was a molecule that it's the first time you've seen it using mechanical energy or something like that?
Rotaxanes? Yeah, the little
Yeah,
spinning guys.
rotaxane. So what exactly do you mean by mechanical energy there? Because surely all the interactions are it all comes down to electrons interacting with protons and stuff at the end of the day. So what exactly is different? Has it just got moving parts or something?
It is, precisely. So you're correct. It is all electrons at the end of the day. What's unusual about these guys is that instead of dealing with what you'd usually refer to as Brownian motion, things just bouncing randomly off each other,
Right.
you actually have a mechanically confined system that still has some degree of flexibility. So it's not ionic or covalent bonds holding these guys together. It's just the fact that you've got, you know, a hoop on a stick that can. I'm trying to avoid making suggestive hand motions. And the rings can spin around. What's cool is I'm going to try and get away from that. If you shine laser light on them, you can get the rings to spin. So you can induce different speeds. So if you see sort of pop science literature referring to molecular motors, they're usually referring to something like that.
Okay.
Connor, was there any greater degree of de vivo process followed at Nuremberg than at Dachau?
Yes, there was a lot more scrutiny in Nuremberg, certainly. Like the picture I showed you of the Dachau court, like that crowd petered out in a few days, so there was no one really watching what was going on. But Nuremberg was the showpiece, like, it was also used as a vessel to try and like democratize Germany. So they really wanted to show that they're following every step of the law, all due process is being shown to show how good a democratic process could be. So there was a lot more careful consideration for their Nuremberg trials.
And
And
that's
it's,
how they just wanted to hang them high.
yeah, well, if you look at the memoirs of the chief prosecutors, they were thinking about their trials as didactic tools, but it never really came across in practice. So I don't know, they're very disassociated with their goals and with what came about, but it was a lot more about get as many as possible.
Yes.
Oh,
And
this is
then
also
Diana.
for Connor. Sorry. Were there many doctors tried at these trials, and if so, was it publicized? Because I know for Nuremberg, like one of the big impetuses for the, I guess, the creation of bioethics, for example, was the Nuremberg trials and all the atrocities that were, experimentation on on prisoners rather, obviously without their consent, kind of brought about that, patient movement and the realization that patients sort of need to consent prior to being treated. So I was wondering kind of what happened with Dachau trials, whether there was that publicity or not.
I don't think there was the same, there were doctors tried, well, relatively lots, and not as many as ours, but I can think of quite a few, because they were particularly active at Mauthaus, and there was a lot of experimentation going on there. Just because the trials overall weren't being as publicized, except for calls for victor's justice and hating them. I don't think their cases have gotten the same press as this. There's a subsequent Nuremberg trial, which is all doctors. So, and that's like where like you said, that code comes from. But I don't think they got the same press. Even though there was that malaria guy, he got petitions from universities across the United States on his behalf, saying that his research into tropical diseases is like the best they had. So.
Diana.
I have a question for Christina. You said you came across the stress and the mystery sort of at a museum. Was it like a solved mystery presented in the museum? Like what did you learn from the museum and what did you learn yourself? Looking into it afterwards.
Oh, okay. Let me think back. Museum allows you to make up your own mind, I think, based on the evidence that they show you. And to me, I mean, they do point out repeatedly that the sock was inside out, the bodice wasn't laced properly. This all points to the fact that she was dressed hastily. And then I combined this with some sort of forensic science kind of work, which then did empirically figure out that she had died from malaria. So I think I combined, I was just using this as a case study to demonstrate how material culture theory can open up something that is dead in the archive.
Sorry.
Oh, good God. And yes, I lost my train of thought.
Oh, it's a mouse.
Thank you.
Maybe I can hold it in 2 seconds.
He's gone.
No, he's gone. He went out the rose wolf window.
Yeah.
Unexpected guest.
Harmlessly problem solved.
He must have been shot. Holy smokes, I'm on the road. Go ahead.
I have a question.
Back, yeah. Yeah.
Yes, sorry, you have a supplementary.
Well, it's actually for Trevor this time.
Okay.
So I was wondering, you showed us a wide array of different and interesting molecules. Are many of these, do they exist naturally in the world, or have these been engineered?
Yeah, well, I mean, a lot of the discipline is sort of inspired by nature. Certainly, certainly in the case of proteins, we see sort of self-assembly going on as the very basis of life. DNA is sort of probably one of the earliest ones to have shown up in life. The actual kind of nitty-gritty of engineering molecules that have self-assembling properties is really kind of a function of our ability to get in there with a really good microscope and look at them. And I'm not talking about a confocal or optical microscope. In most cases, we're talking about an atomic force microscope or an electron microscope. So it's largely progressed as an ability of our ability to get down and see those Legos and decide whether those little hands are making them up right. I think as we kind of get a better and better understanding of what they look like and what they're doing, we can we'll probably start to see all kinds of things made out of them. Could be quite cool.
Okay, I'm going to cut us off.
Yep.
So I want to thank you all for coming, and especially if you could join me in thanking the presenters.